the lush pastures of the British Peak District lies one of the most famous mines in Europe, the Acton mine. The mine provided wealth and prosperity for generations, but now it's flooded, abandoned, and full of mysteries. A dedicated group of scientists decided to reveal those secrets by deploying their latest development. A game-changing robot, an autonomous underwater explorer able to reach caverns unmeasured by man. It's a dream come true after a long and demanding journey. This is the story of a technological breakthrough that can be beneficial for the whole human race. Every mine has its own history. Some have their own historians as well.
I'm John Barnett, I'm an archaeologist, and I've been working in the Acton mines for 25 years. Not all the time. The passage we're in was probably created about 250 years ago. All this was mined. The mines here have always been known as copper mines, and they got a huge amount of copper ores from here. It was one of the biggest mines in the 18th century. It earned the Duke of Devonshire a fortune. But on top of the hill, they started mining in the Bronze Age about 4,000 years ago. The main ore was chalcopyrite, but when it oxidizes, it goes to bright green, which is malachite, or bright blue, which is azurite. In fact, in prehistory, they might not have been mining the copper for bronze, but for pigments, for face painting.
Of course, the Acton mine is not the only abandoned mine in the world. In fact, there are thousands of them in Europe alone. That might sound strange, considering the fact that our lifestyle demands more and more raw materials. Throughout history, civilizations rose and fell depending on their ability to use natural resources wisely. Once upon a time, stones and metal were enough to provide power. But now it's different. Even an ordinary smartphone contains 75 elements, 3 times more than our bodies. Satisfying those needs is more and more challenging for us and for the environment. One of the best solutions would be to reopen abandoned mines where the materials needed can still be mined efficiently using advanced technologies. But which mines? It's hard to decide, as most of them are flooded and hardly accessible for humans. In some situations, robots are very efficient when it comes to carrying out difficult or dangerous tasks. In industrial production and even in mining operations, automation is common. But can robots help us to explore and evaluate flooded mines? Today, assessing the mineral potential in flooded mines is extremely expensive or dangerous, or both. Pumping out the water from all the deep tunnels costs a fortune. Risking human lives with deep diving doesn't seem like a smart option either. Universities and science institutions from all over Europe joined forces to find a solution. A robot named the UX-1. A robot as such should be able to penetrate and map the mines, collect relevant geological data and return back to the surface all on its own. In the UNEXMIN project, every partner is responsible for a defined task. The geological sensors, for example, were developed in Hungary. The pH and conductivity sensors provide information for water chemistry. The radiation meter detects small traces of radioactive elements like uranium. The magnetometer helps detect magnetic ores. And there are instruments specially designed for the UX-1 robot. like the carousel-based water sampler or the cameras which help in mineral identification. Many minerals can be identified thanks to their colour. For example, the azurite and malachite we came across in the Acton mine have distinct spectral characteristics. Illuminating the samples with lights of different wavelengths while recording pictures provides the most detailed spectral information. So detailed that most of the minerals can be identified precisely. All the instruments we've seen have to withstand extreme conditions. For now, the engineers mount all the sensors on one frame to test them underwater. They choose an abandoned quarry as a test site. This clumsy structure is obviously far from being autonomous, but the sensors perform well despite the conditions. To build the appropriate sensors is only one part of the challenge. They need to build a robot as well, able to deliver them to the right place. In Porto, Portugal, there are dedicated people who design autonomous vehicles for dedicated tasks. No wonder they're involved in the UNEXMIN project.
So this is the Robotics and Autonomous Systems Lab of EASME. So we are a research institution, and here what you are seeing is some of our robots and our development laboratory. When people think about robots, they think the typical robot of the movies, the humanoid C-3PO or R2-D2. So our robots tend to be vehicles that are tailored to the task. So if we need a robot in the air, well, it is obvious it is an airplane. If we need a robot at sea, it will be a robotic boat. If we need a robot underwater, then it will be a robotic submarine. For instance, in this case, this is Turtle. It's a robotic autonomous lander. What does it mean? It means a robot that can be used to go to very high depth. It's a very large and heavy robot, and it's also autonomous. So it has, as you can see here, a set of motors, so it can move around. And inside of these cylinders are electronic components, computer, like we have in all of these robots. And this computer is the brain of the system that provides you the control.
UNEXMIN tech team is the host of the first assembly and test of the UX1 robot. Everybody who's involved is here. All the independently developed parts have to fit into a small spherical casing. Not surprisingly, it looks like a spaceship from a science fiction movie. The robot will have to find its way through the forgotten tunnels autonomously. But deep underground, it's impossible to use GPS signals for navigation. Therefore, the UX1 will build its own model of the environment with the help of a set of different sensors. Right now, they're testing and calibrating the so-called structured light scanner. This device, together with different sonars, velocity sensors, and the inertial navigation system, will enable the robot to locate its own position in its own model. The robot has 8 propulsion propellers. Each can work independently and in both directions, giving maximum flexibility of maneuvering. Practically, it's going to be a submarine. So every sophisticated device has to be sealed in a hull against the common enemy of all electronics, water. We've seen that the instruments work fine on a desktop. Now it's time for the underwater test.
From the beginning, the idea was that to build this lab as a multidisciplinary lab for robotics that could be able to have some facilities to do research. For instance, this is our test pool. it's important for developing stuff, because one of the key issues when you are building robots that are to operate out in the wild is that the operation. So for that you need capability of doing tests in the lab, test the hardware, the components, and then we only go to the environment with that.
Luckily, the test pool is only a few meters away. As the robot has to fit through narrow spaces, it's only 60 centimeters in diameter. Even with this reduced size, it weighs more than 100 kilograms. This will cause a logistical challenge in real mines. But for now, the lab's crane is doing the job.
Yes, now it's going down.
The UX1 prototype can move around smoothly, can detect objects precisely, and most importantly, it seems to be watertight. It was just a short dive, but a symbolic and successful one. A real milestone in the process of development. After long months of planning and tinkering, the scientists certainly earned a few moments of celebration.
Let's drink for the first dive of the UNEXMIN robot. So for UNEXMIN. Yes. Cheers. Cheers. Cheers.
It was the first and the last time that the UX1 worked in such cosy conditions. It's time to say goodbye to Porto and shed light on murky mines. The next step is for the team to bring back the robot to the place where its hull was manufactured. Finland. The Kartiala mine is a perfect place for the first mine test. The mine opens from a lake, so it's pretty easy for the support divers to put a frame with mineral samples into the tunnel. On its first mission, the UX1's task is to enter the tunnel from the lake, find the test board, and identify the minerals mounted on it. The robot has to learn to navigate and assess mineral potential under all kinds of conditions. For instance, here the water temperature is only 4 degrees, which is good for the processors and bad for the batteries.
Bring it here to the platform. More or less. I'll try.
Of course, besides the foreseen complications, unexpected problems can occur as well. It's called a test for a reason. Something isn't quite right. The UX1 is unable to submerge. It looks like the robot has to be taken out to find out what went wrong. As it turns out, some of the propellers don't want to work properly. Not a good start. Since nothing's wrong with the mechanical parts, it has to be a software problem.
Yeah, sometimes it starts, sometimes not.
Theoretically, only a few people are needed to operate the robot at this stage. Yet, as we can see, the lakeshore is crowded with experts. Now the pressure is on the coders.
My name is Ramon Suarez. I'm from the Technical University of Madrid, and we're in charge of the guidance, navigation, and control of the UX1 robot. In a normal dive, the system is divided into 2 teams, which is the NEXT team and the UPM team. The UPM team is in charge of controlling the navigation, monitoring the forces, monitoring the velocities, making sure that we're at the right depth that we need to be at that point, and that everything is running smoothly with the control part of the robot. Why do we have so many people right now in a control room? It's just because to check every single system in the robot. So we have to test and debug and validate every single system. So we have a person checking the SLS cameras, we have a person checking the M3 sonar, we have a person checking the scanning sonar, which is, for one person to be debugging and testing all of these systems would be practically impossible.
Finally, the problem is solved and the UX-1 is ready for the mission. It's time for the support divers to get ready as well. If something goes wrong, it's their duty to salvage the robot.
Go, baby, go!
No problem with submerging this time, but the real challenge is still ahead. UX-1 has to find the entrance to the tunnel.
Ok, se quiser aumentar o ganho é esse LED gain.
Want to go half a meter down? No, not yet. Let me first build the map here. You can see it. We are okay. Yeah. I can see the bottom and I'm really in the middle of the entrance. I just want to know, can I go in? Yes. Go in.
As the 3D modelling system has worked perfectly, the robot is smoothly entering the mine and approaching the test frame. The first mine test is a great success after all, which gives confidence to the team to try the robot's navigational abilities in one of the most complex labyrinths nature has ever created. Surprisingly, this exceptional place lies beneath Budapest, the capital of Hungary, also known as the City of Mineral Baths. The Molnar János Cave, a 7-kilometre-long underwater cave system created by the same thermal water which feeds the famous baths. Underwater cave mapping is a time-consuming activity. Divers still use traditional methods and devices. They measure the sections of the fixed guideline with an ordinary tape measure due to the challenges of using laser-based technologies underwater. The direction of the guideline is measured with a compass, and the inclination is calculated from the depth data differences. From these measurements, the explorers can construct a so-called polygon, which represents the simplified structure of the cave. The aim of the UNEXMIN team during the test dives in Budapest is to fine-tune the navigational skills of the UX-1 in this challenging, complex environment, and at the same time help the cave researchers by building 3D models of certain cave sections.
1, 2, 3.
Fortunately, the launch site is easily accessible compared to other underground test sites, but the safe zone ends where the water begins.
Com pêndulo, portanto fala com o Ramon, é olhar para a navegação, para o pitch e com o pêndulo ir a zero.
Every dive is risky, therefore careful preparation is essential. Although the robot is designed to be autonomous, in this case it has a surface connection with the team, so they can follow the data processing and make real-time corrections. Even under the watchful eyes of the team, so many things can go wrong. But so far, everything has gone smoothly. The model is constantly developing as the UX-1 penetrates deeper and deeper into the cave.
So at the moment we have 5 cameras gathering data at the same time. And then you have multiple sensors determining the position, so we need to know that the positioning is accurate, because that determines the orientation of the cameras. So in the end, what we want to have is one single model combining all the data.
On the surface, in the control room, the tension is palpable. There's an unusual extra threat to worry about in the Molnar János cave. The data transfer cable can easily get entangled in a web of guidelines helping the divers, so the UX-1 sometimes needs human intervention during the learning phase. But later on, when everyone has learned the lessons, nothing can stop the joint forces of humans and robots completing the mission.
The rest of our world, we can see everything around us, so we know where we're going. The robot needs to interpret all those things by itself, so it needs to sort of try to understand where it is and stay away from walls and other objects, but also find its way back to the beginning where it started. We don't have any reference system underground, so GPS won't work underground. So it's like the robot is going into a dark tunnel without knowing where the tunnel is going. So it needs to look at its environment to have an idea of the tunnel is going left or right, and basically make its own map as it goes.
Once all the recorded data is processed, the researchers will be able to see the details of this exceptional natural phenomenon like no one has ever seen it before. It was a nice adventure with exceptional results. But the purpose of the project is to rediscover abandoned mines and their forgotten treasures. So why not start the real exploration with one of the most mysterious mines in Europe? The iconic Acton mine. For a couple of days, the teaching room of the Acton Mine Educational Trust is transformed into a state-of-the-art control room by the UNEXMIN team. There is direct access from here into an upper level of the mine.
Okay, cheers. By 1790, they were 300 metres below river level, and all that had to be pumped whenever they were mining there. We know a lot about these upper workings, those that aren't flooding, and we understand them well. But beneath the water, no one's been there since the 1850s.
Indeed, it's too dangerous for humans, but a robot can give it a try.
This is the opportunity, by diving in the water with the submersibles, to find out for the first time what is there.
No one knows what awaits an explorer in the shaft. Therefore, careful initial mapping is essential before the descent. Only a partial amount of the gathered information is used for navigational purposes. The rest is recorded for future analysis, which is not done by the robot, but by humans.
When you're evaluating a mine, the robot collects the spectral images and all of the other instrumental data. And once all of this is kind of cleaned out, then the geologist come into the picture, makes his interpretation of the whole geology of the whole mine.
The robot can operate underwater for up to 6 hours. The post-processing of the terabytes of collected data can take weeks or even months. So the surface team in the control room eagerly watches all kinds of transferred data as they want to get the most out of every second the UX-1 spends exploring the underwater mysteries of Acton.
As a historic mine, this is one of the most important in Britain because it was one of the richest mines in Britain in the 18th century. It's protected by law as nationally important. There's 300 metres of flooded workings and they're very complicated, and we've never known in any detail what's beneath the water, and now we're starting to learn.